Number 17, it says that we have an initial population of 400. After 12 hours, it's grown to 1,542. And we want to know what the zombie population is at time 0. When t equals 0, remember t equals 0 is just the initial amount. That's 400. So really that question is just asking us, do we understand that time equaling 0 is where we start? It's the initial amount, which is the 400. And then we want to find the growth rate constant for this particular strand. So again, this is going to be my continuous model, a times e to the kt. And its growth, we've gone up in numbers, so it's a positive kt. So then we plug in what we know. We know the initial amount is the 400. K is the thing I'm looking for. And then it gives me a time of 12 hours. So I can plug 12 in for time. And if I have a 12 in there for time, the population at 12 hours is going to be the 1,542. And so now I can solve this. I divide each side by the 400. So I divide each side by 400. I'm just going to leave this as a fraction. I'm not going to bother reducing it. It might divide evenly. It might not. If it divides evenly, that's great. You can leave it as a decimal. But I'm just going to leave it as a fraction for now. Over here, e to the 12k. And now I take the natural log of each side. And what's nice about our continuous model is the natural log and e cancel out. So what I'm left with is the natural log of 1,542 over the 400 simply equals 12k. And now I can just divide each side. Let me bring that up here. So now I just divide each side by 12. Okay? Again, this is a job for my calculator. I plug it in. So I get 0.112. We'll go 3 decimal places on this one. On the test, make sure that you round to the number of decimal places specified. And that's going to be per hour because my time was in hours. And it's important to remember that unit is attached there. So when I look at part C, in part C it says what's the population after 3 days. So now I still have my initial amount is the 400. I've got E, I've got my K value now at the 0.112. And then time, I can't plug a 3 in here because the K value is per hour, which is why I wrote that down. So that means my time needs to be in hours. So I need to multiply this by 72 when I go to plug this in. And this is just a plug it into my calculator problem. So I find out that the amount is going to be the 400 times e to the 0.112 times 72. So I get something that looks like this. I'll keep it at 2 decimal places. Okay, and that's it. That's the number of zombies. A couple partial pieces, and that's fine. If I look at part D, it asks when will the population reach, and obviously that comma is the wrong place. It should be 1 million. So what I want to do here, I've still got the 400 as the initial amount, e to the 0.112. I'm looking for time this time, and I want to know when this thing is going to equal the 1 million. So I'm going to solve. I'm going to divide each side by that 400. And this time I'm actually going to plug this into my calculator just because I know that's going to divide pretty nicely. Gives me a 2,500 equals e to the 0.112t. I take the natural log of each side, which is the same process we've been following. Natural log and the e cancel out. So I've got the natural log of 2,500 equals 0.112t. And now I can divide each side by the 0.112. So I find out that t equals natural log of 2,500 divided by the 0.112. So it's approximately 69.86. And again, the units are important here. That was per hour for my rate, so this is going to be in hours. Okay? So make sure you put units on there, especially if you change it to something else like days. All right? For this one, it says a virus is wiping out the human race. After 1 week, a town with an initial population of 133,427 people now has only 109,406 people left. And we want to know how many are going to be left at the end of the year. And this is really a two-part problem. The first thing we need to do is find the k value here. So again, we start with the initial amount is this, e to the k, and this time it's decay because the amounts are going down, negative k, and then time. I can plug in for time for this one. I have really two options here. After 1 week, I could plug a 1 in here and do this per week, or you could plug a 7 in here and do it per day. Either one should be fine. I'm going to do it per week to start. Maybe I'll show the other one if I have a little bit of time here. So now I want to solve this for k. I'm going to divide each side. So now, once again, I'm going to leave that as a big giant fraction. It's going to be easy enough to plug into my calculator the way it is anyway. And then I've got e to the negative k. I take the natural log of each side. Natural log and e cancel out. So I have the natural log of the 109,406 over the 133,427 equals the negative k. And then I just divide each side by a negative. Okay, by -1. And again, this is just a job for my calculator. I plug it in. So when I do that, I get something that looks like this, a 0.1985 is what I'll round it to. I'll go 4 decimal places to give myself a little bit of accuracy here. So then if I want to know how many are going to be left at the end of the year, well, I know the initial amount, and I know e to the negative k. My k value was the 0.1985. Multiplied by time, well, here, this one, because I left it as a 1 when it was 1 week, this is per week, which means I need to plug time into weeks. In a year, there are 52 weeks, so I've got to plug a 52 in here. And now, again, this is a job for my calculator, so I'm going to plug this in, the times e to the and it gives me somewhere approximately around 4.39, so about 4 people left. Again, if this thing is not combated in some way. Now, out of curiosity, had we solved here by plugging a 7 in and done this per day, just to show you the difference here, per day I would end up taking that natural log of the new amount divided by the original amount. If I were to solve this with the 7 in there, I end up getting something that looks like this for my k value, 0.0284 when it's rounded off. And when I plug that in, with time being 365 for days, because this is per day, the amount of people that I end up getting is a 4.2, which rounds to 4 people either way, okay? So keep that in mind. If you have a different time signature for the k value, you'll get a completely different k value, but your answer to the second piece of this thing should be pretty much identical for somebody who did it in weeks, all right? If you look at something like this, this one, scientists want to determine how old Superman is, and by what they're going to do is they're going to find out the age of the kryptonite that was with him when he crash landed. So again, the first thing we're going to need to do this one is identify the k value. And we're going to use that using the half-life, all right? It tells us that the original amount present was the 4,200 grams. And again, it's e to the negative kt. We're using the half-life. It tells us that the half-life is 300 years, which means if I plug a 300 in here for the number of years, after 300 years, we should have half the amount left, which means we'd be down to 2,100. of this stuff. And now we can solve this for k. We're going to divide each side by the 4,200, which is going to give me a 0.5 equals e to the negative 300k. And now I take the natural log of each side. Natural log and e cancel. I've got the natural log of 0.5 equals a negative 300k. And then I just divide by the negative 300. And so this is going to establish my k value, which essentially breaks this down per year then. So I've got the natural log of 0.5 divided by the negative 300. So I find out that my k value is approximately 0.00, and we're going to go 231. That's what I'm going to round it to. And again, that's per year. And that's why I've done this. With the half-life being 300 years, I have this in increments of 300 years. I wanted it in increments of 1 year to make it easier to calculate. And so now, if we look at this, it says that the sample contains 3,500 grams of the substance. So if I want to find out how old this is, it had 4,200 originally. It's down to 3,500. I know that the decay rate constant is 0.00231. And now I want to solve for time. So I'm going to divide each side. So I divide each side by the 4,200. And again, you can just leave this the way it is. I'm going to immediately reduce it to 35 over 42 because those zeros can just go away. And of course, I can reduce that further. But there's not really much of a point in reducing it further. And then I take the natural log of each side. Natural log and e cancel. So I've got the natural log of the 35 over 42 equals the negative 0.00231. And now I just divide. And what this is going to do, it's going to give me the age of the kryptonite, which started breaking down when Superman entered our atmosphere, which should give me his approximate age. So I'm just going to plug this into my calculator. So it turns out that he is approximately 78.9 years old. So we'll see he's about 79 years old.